So I don't have any research to report. I did get a big chunk of the ladle stuff detect, and it's in the repo. It's also uh, I've got it set up so that it works with Overleaf. So Overleaf is a group, a tech editor that was recommended to me by Christian Williams. So that way Mike and I can continue to work in sort of on the document in real time. But that's so it's a lot easier to read now. The Google Doc was a little bit I don't know. It's Google is not made for mathematical typesetting, so it's that's all done. But it's mostly just typesetting, not any sort of movement. The one thing I can say in terms of sections that we're going to add to the document, Mike pointed out that we should observe in the document that you could trampoline the structures that we introduced. So we introduced these structures for taking apart the terms, the computational terms that are frozen without resource, right? So for K's that don't have R's, we have a parallel par construct and a series par construct, which allows to take apart the frozen computation and rewire it either in parallel or in series. So that's you can see that as adding terms to the language, but as long as your language is computationally complete, you can always boil those away, right, by just implementing them as data structures in the language that you're typing. And then that gives you a way to have the type system work directly on the language as opposed to, on an enriched form of the language. So we'll be adding that section to the paper because it's a nice it's nice in the sense that the construction gives you an algorithm for the language as it is, as opposed to a modified version of the language. Does that make sense?
Well, not completely for me. So
okay, so if you look at the construction, what the construction does is it says, all right, you've got some K construct like a par in the case of row calculus, or an application in the case of the lambda calculus, that is the basis for the left-hand side of a rewrite rule. And the first step is to modify the rewrite rules so that they have to have a resource in order to rewrite. And if they don't have the resource, then the rewrite is effectively frozen, right? So the construct, the par or the application or whatever it is that is a regex expression, is frozen. It can't go forward. Does that much make sense?
Yeah.
So then the question is, now that you've got a frozen computation, can you do anything with it? Can you extract the data and change the computation? Right. So that's right. So the freezing part is called reification. You reify the computation into data. But if you can't modify the data, then it's sort of limited in its utility.
Yeah.
So we introduce two new terms. One is a par term, which when you cut it against the frozen computation, so it has two terms inside it, right? So K is a binary thing, so it's got two terms, which would normally be a part of a reduction. So par also has two terms, and those terms are of the opposite polarity, right? Meaning that if you run, well, in the case of the par, the terms are of opposite polarity. So if um,
Can you say opposite polarity? I'm not sure that I understand.
yes,
In case of par.
yeah, so it means that their types are essentially a form of negation of the other in this rely guarantee thing.
Okay.
Right. So it's easier to see if you look at the document, but so if K has the left hand side of K is of type tau, and the right hand side is of type tau prime, then in the par that it gets cut against must be of type tau perp, and the right hand side must be of type tau perp prime, or tau prime perp. So now when you cut them, you'll cut the tau with the tau perp, and the tau prime with the tau prime perp, and this guarantees the property. Does that make sense?
Yeah, I can see it.
Okay, good. So that's the in parallel form, right? So T goes with T prime, U goes with U prime, but you could also do it in series. So you have the T and the U, and you have the T prime and the U prime, but you cut T against U, and then you cut U prime against T prime against U prime, and then you cut the two results that way. So then your types will be different. They'll be arrow types, and it's much easier to look in the document to see rather than me to say them in English. But just look in that document is in terms of what the arrows have to be in order for the property to be guaranteed. So that's running the circuit in series as opposed to in parallel.
Mm-hmm.
Okay, so
this makes sense.
Okay, so the important thing is that these two new terms, the par and the serial terms, they're not part of your original language, right? They're terms that we introduced as a part of the reflection machinery. But if the language that you're typing is computationally complete, it's Turing complete or it's functionally complete, then you can always implement the par and the serial terms in terms of data structures using the existing language features. And so that means that you could boil away. You don't have to have these things in your so your type system. So you start with the intermediate language that has these terms, and you type everything, and then you get rid of those terms in terms of via the introduction of the implementations of those terms in the language. And so now your type system works just on the original language that you started with, not on this intermediate language that we produced. Right. So it's just it's a nicety in the sense that it it cleans things up. It means that, you know, ladle works on the language that you hand us, as opposed to on an enriched form of the language.
Okay, okay. Now I don't understand completely, but I see what you mean. Yeah. Okay.
Cool. Yeah.
And this works. All you said this works only if we are not using R or.
No. All I was saying was that you the K constructor, if you don't have the R present, the K constructor becomes a means of freezing computation.
Yeah.
Right.
This is like a quotation, right? In a sense.
It's like quotation, but I mean it maps directly onto blockchain, right? What it says is that you know, this is a contract that's not been supplied any gas. Right. So the R resource is like gas or flow.
Yeah. I see. So with cut operators for serial and par, you're saying we don't need them. We can operate on K without this special terms constructor.
No, what I'm saying is that it's a little bit more nuanced. You can implement the par and serial terms via other features of the language. So like in Scala, you could just make a data structure called par and a data structure called serial, right? And then when you implement, then when you do an application, you know, right, that application would cut your function against, you know, a par term or a serial term, right? So
Okay.
now you're not going out, now you're not typing a Scala plus that has these special constructs. You're just typing ordinary Scala programs.
Okay, I see. And we are like we are trying to apply ladle on Scala in this example.
In that example, we're applying ladle to Scala. The point is that you can apply ladle to anything that is a computational. In fact, it doesn't even have to be computational. It can just be an algebra. It doesn't have to have rewrite rules. And in which case you get, you know, a typing system for the term constructors, you know, for the algebraic constructors.
Yeah. Okay, this makes sense. Okay, thanks for explanation. Yeah.
Sure. No, thanks for the question. Anyway, so that's the one little bit of advance that we've made, and then Mike is the other section that I'll have to add to the draft is the categorical interpretation. So the angle that we're pitching the paper at in this setting is in the early 90s, Bramsky, Gay, and Nagarajan proposed a flavor of categories called interaction categories. And what they were after was an axiomatic account of interaction. But unfortunately, they didn't really axiomatize interaction. What they took as their centerpiece, right? Their conceptual framework was linear logic, and then they built notions of computation around that, but they didn't really axiomatize interaction itself. And it's really the notion of interactive computation is actually really important. It's a fairly foundational shift. It's a tectonic shift in thinking in computer science, right? If you compare state machines and Chomsky grammars and Turing machines, which are sort of the first wave of computational models, with lambda calculus and pi calculus and row calculus. So on the left-hand side, what we have are things that are essentially unaware of the computational environment, meaning that the model of computation does not include the environment of the program. It's not a part of the reasoning apparatus. In compositional models of computation, such as the lambda calculus, the environment is a part of the mathematical apparatus. So you can, meaning the environment of the program. You can, interaction means you can split computations into two parts. One is the program and the other is the environment. And in many cases, that split is kind of dual, in the sense that you could also flip it round and see the environment as the program and the program as the environment, right? So that duality is quite interesting. And this whole idea of having an explicit model of the program's environment in terms of the 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 mathematical model that you've got is powerful, right? And we argue that this is the notion of interaction that needs to be captured, and that basically has a very simple axiomatic characterization, right? So we start, rather than from linear logic, we start with rewrite systems. The left-hand side of the rewrite rules have to be bipartite, right? They have to have a term constructor of at least arity 2, so that it can be split into one part, which is the program, and the other part, which is the environment. And how like whether or not there's a duality there is part of what makes the whole thing interesting. So we're from that perspective, we generate the rest of the ladle construction, right? The ladle construction basically says, if you add to an interactive system this resourcing idea, then you can get the whole rest of it. It does depend on the fact that the properties are idempotent. So you have, the construction becomes much more nuanced and subtle if you don't have properties that are idempotent. Another way to think about those properties is that they're persistent. All right, so you need that K of a thing and the property you're trying to events is equal to K of the thing. So this works for like the identity, which would mean that the two structures are isolated from each other, or you can use it for banged properties. So and by bang I mean, like the replication operator in the pi calculus, or the bang in linear logic. So when you have properties like that, they're also persistent or idempotent with respect to K. So that's the demand that this type system makes on the kinds of properties that you can establish. So what that means is that you've got a sort of recursive supply of whatever it is that you're, a regenerative supply of whatever it is you're trying to establish, right? So that's a key factor in the property that you that this type system will give you. So, and once you have all of those elements together, then you can build this type system, and that type system gives you a category where intuitively it's a little bit more nuanced than this, but intuitively speaking, the types are the objects in the category, and the sequences of sequence, which are proofs, are the morphisms in the category. And we argue that this is an axiomatic characterization of the interaction categories. So it will have, like in certain special cases, it will have a flavor of linear logic. So you'll recover the Abramsky notion of interaction categories, but this now covers a much wider range of phenomena, right? It allows you to go after realistic programming languages like Scala and JavaScript and things like that. So that's the point. And moreover, this goes back to what I was saying since 2016, which is now that that there's nothing special about the EVM. There's nothing special about any of these. If you want a smart contracting system, this makes it entirely algorithmic. Like whatever programming language you want, we can algorithmically add a notion of gas and get a type system that allows you to reason about gas constrained programs. So that's the key idea here. So from a blockchain perspective, this completely commoditizes. There's nothing special about gas constraining programs, whereas there is something special about whether or not your computational model supports concurrency or things like that, right? That's those can now be disambiguated and reasoned about separately. So and again, this is the point I've been trying to make for several years now. Anyway, so that's the that. So does that make sense? Do you understand what I'm driving at?
Yeah, I think it does. So I'm thinking that how can we make like simple example for we need to know the environment and also the program, right? These are two components that we need to know so we can apply and get some kind of resource constraint, right? Is this maybe simple?
Yeah. So the simple example that I've given is actually in the paper. So we start with the simplest possible example. So you've got a K. You've got only one rewrite rule. You've got a K, and you only got one generator apart from the identities. All right, so that's as simple as possible example, right? And that's the one we go through, and then we go through examples of increasing complexity. So it turns out that the row combinators is the next level of example in terms of simplicity, right? So we give so in the paper we've already given a presentation of the row combinators, and so that's the next level of example, and then the SKI is the next level of example in terms of, but in terms of complexity, SKI is actually more complex than the row combinators, because you've got different, you've got interaction rules that involve three things, right? So S involves three things, not
Yeah.
just two, and so you get so you know, the when you instantiate the type system, it's more complicated, but it, you know, it still works according to the rules. So that's the, you know, that's what we do in the paper, is to go through those basic examples. I mean, and you have to understand that you know, those examples are already relatively complicated. You know, once you apply this to a language with as many features as Scala, you know, your only hope is to do this algorithmically, because Scala is just super complicated, and JavaScript is also super complicated. So the only hope to do this is to do it algorithmically. It's just, you can't do it by hand. It's way too complicated. So you can do it by hand in these simple examples like the row combinators or SKI. But realistic programming languages with all these features, you know, it's just not possible. You must have computational support to get it done, and that's what the ladle algorithm provides, and it provides it in a way that one can rest assured that the results will be correct.
Yeah. And for example, in JavaScript, we only have one type of reduction, right?
No,
Or
you have multiple types of reduction. You have application, which is,
mhm.
but the reality is that application is polymorphic in JavaScript. So there are lots of different ways that thing is going to be interpreted. And in particular, the place where it gets a lot trickier is in the arithmetic. So once you get down into the realities of how arithmetic works on computers, with all of the different failure modes, it's a lot of work. Like, to get the details right is a lot of work.
Okay. Yeah. And do we think about different reductions? I mean, we have different rules of reduction depending on environment, which is not visible in today languages, right? But
So
we
again,
care about environment.
no. Remember, all we're saying is that your reduction rule has to have on the left-hand side a two-part constructor. We're not saying that you have to consider all deployment environments or anything like that. But what we're saying is, like in the case of application, you can think of the function as the program and the arguments as the environment. Alternatively, you could think of the arguments as the program and the function as the environment. In the case of the par constructor, you can think of the for comprehension as the program and the output as the environment. Alternatively, you could flip it around and you could think of the output as the program and the for comprehension as the environment. but this is this is what I mean by program and environment.
I see. Mm-hmm. Yeah, this makes sense.
Yeah, it's very scoped, because what it says is that, you know, environments can't be any more complicated than programs, right? Because the only thing you can put in, you know, one side of the constructor is a well-formed lambda term, or a well-formed pi term, or a well-formed rho term. So you see?
Yeah.
Right. So
Yeah.
it basically says, you know, we're not, it's sort of a closed world hypothesis, in the sense that the only kinds of phenomena we're admitting are phenomena that are describable by the computational system you've got, right? So in the case of the lambda calculus, the only kind of phenomena we're admitting are are lambda terms. That's it. Nothing else. Nothing exists outside of lambda terms. Or in the case of the rho calculus, nothing exists outside of rho terms.
Oh, I see. So it's possible to apply a ladle to Scala, for example, and still write Scala code.
And still what? I couldn't understand the last.
Still write Scala code with
Yes, exactly.
ladle type system. Oh,
Yes,
nice.
that's the point.
Nice.
That is entirely the point.
Oh, this looks great.
Yes, exactly. So it works for, and it works for everything that is like, and you have to get to really exotic models of computation before ladle stops working. So in particular, one of the things that we've been wanting to make sure that the scope includes quantum like models of computation. So I mean, we still have work to do, but I believe at this moment that it extends to models of computation that include quantum computation.
Nice.
Right. So this is why it's taken. Like, I could have produced a paper in 2006 that says, you know, it works for this, right? But what I wanted was but I could see the scope of the algorithm, and I wanted to make sure that we had a framework in which people could see the scope of the algorithm, right? People could understand that you know, this allows us to apply the algorithm to basically any of the, you know, mainstream models of computation, or any of the, you know, slightly outside models of computation. You know, it's basically got, you know, probably a 200-year scope in terms of the models of computation that people are likely to consider. So out beyond, you know, I mean, certainly any form of molecular computation, ladle can apply to that. Yeah, I mean, there's going to have to be some significant conceptual revolution before we find a model of computation that ladle doesn't apply to.
Nice. And for the input to ladle, if for example, I was listening Simon Marlowe. They're developing like a database of semantics of languages in Facebook, and I was thinking, oh, this is very nice specification, and can we use this as an input to ladle and generate a type system for all of these languages?
Yeah, that's the idea. Eventually, someone has to come up with a format that everyone agrees on, right?
Yeah.
Right. And so what we used is the essentially graph-enriched Levier theories. Now, the trick here, when you're talking about these kinds of things, is like Levier theories don't really deal with nominal phenomena. So things like, like abstraction in the lambda calculus, or the sort of pseudo abstraction in the pi calculus. So now Clauston has shown how to extend the Levier theories to include nominal phenomena. But the point is, it's modular. So here's a rough and ready way to think about it. Levier theories correspond to monads, and which is one of the reasons why we chose Levier theories. And then the rewrite parts of them also correspond to a particular kind of monadic extension. And then you can think of the nominal phenomena as also essentially captured by some monadic machinery that you can compose in. So basically you stack a bunch of monads together, and ultimately you get your notion of computation. And this is very much in alignment with how Maji thought about the use of monads, right? Is essentially you stack a bunch of monads together to get the features of your language, right? And so we're taking that perspective fairly seriously, and as long as you have some kind of monadic presentation, then some flavor of Levier theory is going to be a reasonable format for expressing your semantics. So that's the sort of sloganized version of what we're of the program. And ultimately you have to come up with some answer here, so that you can make specific statements, specific and provable statements about the algorithms, right? So I need, like, if you go through our paper, we have to say, how do you present to the algorithm the input of your computational system? So we take as input a particular kind of enriched Levier theory, and then we operate on that Levier theory, producing a new Levier theory, and then in two stages. So first we produce the resourced version, then we produce the contextualized version, right? And so we get this version of the Levier theory that has all the pieces we need in order to calculate the type system. And then we show that Levier theory has a reduction back down to the original Levier theory. So the type system applies to the language you started with. But I mean, Levier theories are, they're not going to be friendly, I think, to most programmers. So we're going to have to come up with some format that programmers find appealing and intuitive, that have a mapping onto. I've got to jump off now, but I'll I think we're at a natural close. All right. Chat later.
Thanks, Rick.